Welcome to The Explainer. Today, we're taking dense, kind of intimidating circuit schematics and translating them into a completely intuitive visual journey. If you've ever stared at a custom board and just wondered how on earth a device manages its power so perfectly, without melting into a smelly puddle of plastic, well, you are exactly in the right place. We are going to completely demystify the DC to DC buck converter.
Okay, let's just dive right into our roadmap for today. We'll be hitting 1. The power conversion problem. 2. Inside the buck converter. 3. Mastering the duty cycle. 4. Continuous versus discontinuous mode. 5. Taming the voltage ripple. And finally, 6. Designing your own converter.
All right, let's start with section 1, the power conversion problem.
So, here is the ultimate engineering headache we've all run into at some point, right? Say you've got a really robust 40-volt battery, but your delicate electronics only need 18 volts to run. How do you actually step down that power without turning the extra 22 volts into this massively wasteful mini heater? That's our core challenge.
Now, back in the old days, we relied on a potential divider or a resistive circuit. And the problem with that? The efficiency was absolutely terrible. I mean, it literally just burned off that excess voltage as raw heat. It's kind of like driving a car down the highway by keeping your foot glued to the gas pedal while simultaneously riding the brakes just to control your speed. Just terribly wasteful. But modern electronics, we use switched mode operation. In this setup, a transistor acts as a super fast on-off switch. Because that switch is only ever fully on or fully off, there is practically zero power loss. It's a game changer. But while this brilliantly solves our heat problem, it introduces a brand new headache. A really choppy pulsing voltage that our sensitive microchips will absolutely hate.
Which brings us to section 2, inside the buck converter. Let's actually look at the anatomy of our solution here. We've got our switch, and to that we've added a diode, an inductor, and a capacitor. You can really think of the inductor and capacitor as physical shock absorbers for your circuit. Like if electricity is water blasting through a pipe, the inductor amazingly stores the actual momentum of that water, and the capacitor acts like a giant reservoir tank. Working together, they take those violent, pulsing spurts of energy from our fast-acting switch and smooth them all out into a nice, steady, reliable stream for our load.
And this setup creates what is essentially the heartbeat of our circuit. When the switch is on, energy flows directly from our source, feeding the load while simultaneously charging up our inductor with magnetic energy. But the absolute instant that switch turns off, the source is entirely disconnected. The inductor, though, it says, hey, not so fast. It releases its stored energy, pulling current right up through that forward bias diode to keep the load happily fed. And we are just constantly bouncing back and forth between these two states, thousands of times every single second.
Moving right along to section 3, mastering the duty cycle.
So what is the duty cycle? Represented by the letter D, it is simply the ratio of the time our switch spends in the on position compared to the total time of one complete switching cycle. This really simple ratio is basically the master dial for controlling our average output voltage.
And the math here is honestly pretty elegant. Our average output voltage, Vout, is literally just the duty cycle multiplied by our input voltage, Vin. Need exactly half your input voltage? Boom! Set your duty cycle to 0.5, meaning that switch is closed 50% of the time. In an ideal circuit, it really is that straightforward.
The actual technique we use to achieve this is called pulse width modulation, or PWM for short. Instead of changing how fast we flip the switch, the frequency, we keep that frequency totally fixed. All we do is stretch or shrink the actual width of that on pulse. And by keeping the switching frequency locked in, it becomes so much easier to design our inductor and capacitor filters to target and smooth out the very specific electrical noise the switching creates.
All right, section 4, continuous versus discontinuous mode.
So, continuous conduction mode, or CCM. This is generally exactly where we want our circuit to be. It's an operating state where the current flowing through our inductor never drops all the way down to zero during the switching cycle. Going back to our water pipe analogy, it's a constant, totally uninterrupted stream of water that never runs dry. That makes the whole system incredibly stable and really easy to predict.
The really crucial takeaway here is the stark contrast between these two modes. In CCM, which happens at higher loads, the operation is super smooth. Our simple Vout equals duty cycle times Vin math works perfectly. But here is the real danger zone. If your load drops too low, let's say your device suddenly goes to sleep, the current in the inductor can actually drain all the way to zero before the next cycle even starts. This is discontinuous conduction mode, or DCM. And once you dip into DCM, the math completely goes out the window. Your output voltage suddenly becomes incredibly unstable and directly dependent on the load itself, which means you need far more complex control logic just to keep it from spiraling out of spec.
Let's move to Section 5, Taming the Voltage Ripple.
When you graph the inductor current, you get this very distinct triangular waveform. That shape is the literal physical manifestation of our switch opening and closing. As the switch turns on, the current ramps up to a peak maximum. When it flips off, the inductor discharges and the current ramps down into a valley. That total distance from the peak to the valley, that is our current ripple. And if that ripple is too massive, our capacitor just won't be able to smooth it out, and our sensitive 18-volt microchip is going to get absolutely hammered by rapid, dangerous voltage fluctuations.
And finally, Section 6, Designing Your Own Converter.
Look, we just have to face the music right off the bat. There is no such thing as a perfect, magical converter. Engineering is just a series of crucial, real-world compromises. If you choose a very high switching frequency, sure, you get to use a physically smaller inductor and capacitor, which saves precious space on your board. But your switch is going to generate a ton more heat from cycling on and off so rapidly. If you go the other route with a lower frequency, your efficiency goes up, but now your components are getting bulky. And if you absolutely must have a tiny voltage ripple for a sensitive load, you're going to be forced to use a physically larger capacitor to absorb it all. But the good news is we can take all those heavy, terrifying engineering flowcharts and distill them down into a surprisingly simple, actionable 4-step recipe for your next build. Step 1, choose your switching frequency based on your physical size and heat constraints. Step 2, calculate the required duty cycle for your target voltage. Step 3, size your inductor perfectly so you always stay above that zero current boundary and remain safely in continuous mode. And finally, Step 4, select a capacitor large enough to actually absorb your specific ripple limits.
Let's actually plug some real numbers in and go back to our original 40-volt battery problem. We want to step it down to 18 volts, and let's say we're operating at 50 kilohertz. The math instantly confirms our duty cycle needs to be 0.45. By plugging in our load resistance and our frequency, we find the absolute minimum boundary for our inductor is 82.5 microhenries. Now, to be safe and absolutely guarantee we stay in CCM, we'll add a 25% margin, settling on a nice, robust 103 microhenry inductor. Then, to keep our voltage ripples strictly under 1%, our final equation tells us we need a 26.67 microfarad capacitor. See? The theory literally translates directly into exactly which physical parts you need to pull from the bin.
Just to cement the whole shebang, let's run through the key takeaways. Remember, your duty cycle is the master controller for your overall output voltage. Your inductor acts to control the physical current ripple. Your capacitor steps in to smooth out the final voltage ripple hitting your device, and your primary design goal for a robust, reliable system: maintain enough minimum current to stay safely nestled within continuous conduction mode. So you've got the mathematical recipe down. You know exactly how to step down voltage with incredible efficiency and precision, and how to shrink your components to fit onto super tight board spaces. But remember those trade-offs we talked about? As you push those switching frequencies higher and higher to make your gadgets smaller, how will you manage the invisible thermal heat boundaries that are guaranteed to crop up in your next design? That, my friends, is the real art of power engineering. I highly encourage you to step away from the theory, get out a real breadboard, and actually test these thermal limits for yourself. Thanks so much for hanging out with me on this explainer, and I'll catch you in the next one.